you, Gregor, and thanks everyone for being here. I think Gregor's voice and lack of enthusiasm is a good testament to how tired we all are. But so I'll try and be gentle this morning. Actually, no, I won't. But you know, I was told I'm, and the organizers might regret this, but I was told that the last talk was supposed to be more of a research-oriented talk. So I'm actually giving a talk that I've given a couple of times in other places about some work that I did for once. And the context, well, the motivating question is what I would call a geography question, is given Y a three-manifold, and mostly I will be thinking about a rational homology sphere. What can we say about the set of whose boundary is Y? And yes, you can complain. This is not a set, fine. Let's say up to diffeomorphism. Let's not get caught up in these things. And this is a question with a long history of answers. First of all, you might ask, is this set empty? And the answer is no. And this is Rochlin's theorem, omega 3 equals 0. Every three-manifold bounds a four-manifold with the right adjectives. But then you might ask, you know, can we always find something that is simply connected? Answer is yes. This is, I guess, the Licorice-Wallace theorem. That it's even better. There's always a geometrically simply connected four-manifold. There's always a four-manifold built using only two handles that you can fill any three-manifold with. Something like spin. Filippo, who's not here, yesterday. Oh, you're here. You arrived late? I didn't see. You weren't there like 2 minutes ago. Filippo yesterday talked about spin structures on surfaces. You can ask whether there's always a spin four-manifold bounding a given three-manifold, and the answer is still yes. This is omega. Actually, there's something even stronger. Omega 3 spin is 0. I don't know who to put this to, sorry. But this says that every spin C structure on a three-manifold is the boundary of a spin four-manifold. Then you can ask, well, what about the intersection form? Because I like intersection forms. So there always exists a negative definite four-manifold in this class. And the answer is no. I think that the first proof is to Donaldson. And this is the first point in which, at least for integer homology spheres, the algebraic topology, the topological category and the differential category differ. Because here I'm working with, let's say, smooth W smooth. Donaldson proved that the Poincare homology sphere with one of the two orientations, and the one that I want is the one oriented as the +1 surgery on the trifoil. This never bounds a definite four-manifold, a negative definite four-manifold. And the question that I would like to answer today is whether there always exists one that is negative definite or one that is positive definite. And here the answer is actually yes for for some classes of three manifolds. So for instance, length spaces, okay, this is not very much. Ciphered fibered, we're going to see in a second what these are. Double covers of alternating knots. All surgeries on knots in S3, and so on. So pretty much every manifold that you can think of constructing, like the first three constructions that come to mind, none of them works. So nevertheless, the answer is no. And there's a, so this was proved by Freuchov under some additional assumption, under a mild assumption on H1 of the four manifolds that we consider, namely that there's no two torsion. And then it was proved by Nozaki, Sato, and Taniguchi. This might still be unpublished, but it also might be in his thesis, and I'm not exactly sure. This was done, I think, in 2019-ish, who proved that a certain three manifold does not bound, actually, a certain integer homology sphere does not bound either a positive definite or a negative definite four manifold using, on the one hand, Heegaard-Floer, and on the other, instanton theory to sort of, they used one of the two to prove that something cannot bound something negative definite, and the other one to prove that it cannot bound something positive definite. And then there's further work of Lidman, Daimi, Lidman, and Miller, Eismeyer. This is one person, and these are two people, who also used Heegaard-Floer homology and instanton-Floer theory, but they also have the fact that the three manifold is an L space. So Y, three manifold Y, is an L space, and this has the nice corollary that it implies that this three manifold, so let me call this the YDLM, YDLM does not embed in any four manifold that admits a symplectic structure. So somehow there's a parallel question to this question, which is, given a three manifold, in which four manifolds can you embed it? For instance, which manifolds can you embed in S3? Which manifolds can you embed in CP2? You can ask for larger classes of four manifolds, which manifolds embed in symplectic manifolds or complex surfaces, and they found the first example of a three manifold that does not embed in any symplectic four manifold, which is a fairly large class. Great. So I promise that there is some work of mine coming up. So this is joint work with Kyle Larson from a couple of years ago. I think it's just been published, and I kind of lost track. This wonderful three manifold does not bound a definite four manifold. It's an example, but it's a rather concrete one. Also, their examples are rather concrete, to be fair. And who is this guy? Yep. Who is this guy? So M B P1 over Q1 Pn over Qn is notation pretty much universal for Seifert fiber 3 manifolds. And to be very concrete, our 3 manifold is obtained in the diagram So I'm taking this 4-component link, an unknot, and 3 pairwise unlinked meridians. And I'm doing surgery, so I'm doing Dane filling. So I'm carving out 4 solid tori, and I'm regluing in 4 solid tori, so that the meridian of the meridians of new solid tori are glued onto the curve of slope -2, minus 23 over 22, minus 17 over 3, and minus 15 over 13. And for those of you who are more singularity theory inclined, this is the link of the singularity of a surface in C6, which I think is defined by 9 equations, something like that. So this is a nice 3 manifold, which is Seifert fibered. And in particular, it does bound a definite 4 manifold. It bounds a negative definite 4 manifold, which is obtained by somehow expanding this rational surgery representation into an integer surgery representation that I don't want to draw because it's rather large. And P is sigma 235. This is your favorite 3 manifold, which is not an L space, a length space, and that is not the 3 sphere. This is, in this notation, this should be M minus 2, 1 over 2, 1 over 3, 1 over 5. No, 2 over 3. Very concretely, this is the intersection of this hypersurface in C3 with the 5 sphere of radius 1. C3. Even more concretely, this is -1 surgery on the left-handed trefoil. Which, by the way, is this same manifold here, just with the opposite orientation. So this is minus P. And minus is just orientation reversal. So each of the 2 pieces, or the 4 pieces, depending on how you count, in this equation bounds something definite, but they bound something definite with the opposite orientation. And when you do the connected sum, you have no control of what happens with intersection forms. Right. The only other thing that I wanted to say is that we'll maybe see in the exercise that this is a homology RP3. That is to say, its first homology group of this manifold here is Z over 2Z. And this is an integer homology sphere. So when I do the connected sum, I still get an integer homology RP3. Yep. Yeah, so what I want to say is if you take the connected sum of two three manifolds that each bound a negative definite four manifold, when you do the connected sum, you know that the connected sum bounds a negative definite four manifold because you can take the boundary connected sum of the two four manifolds that you're given. If they were to bound or definite four manifolds with the same definition, yeah. In this case, one of them bounds something positive, the other one bounds something negative. So you can't say, oh, it bounds something negative for obvious reasons, or it bounds, yeah. Yeah, that was a bit convoluted, but thank you. Right. So there's a technical statement behind the statement of the theorem, which is what I think is slightly more interesting. That is, if y is the boundary of W is negative definite, and y is an integer homology RP3. So it has the same homology of the three manifold that we're considering. Then, okay. Y is an integer homology RP3, so it has two spin C structures. So I have two correction terms. Because I have two spin C structures, so I have two correction terms. And then their sum is always at least 0. And if equality holds, then one of them, let's say T0, is 1/4, and the other one is -1/4. A statement like this should tell you something about how I'm going to prove things, because there was a similar statement somewhere in one of the previous lectures that had a similar feel to it than the statement that I have. So maybe this is theorem 2, this is theorem 1. How do you prove theorem 1? So I'm already way ahead of Emmanuel here. I have two theorems, and I'm going to do one proof. And I'm only 20 minutes into the talk. So of theorem 1, well, we just need to compute the correction terms of that manifold. So let me call this. How do I want to call this? I want to call it N, because it does not bound something definite. So in the two spin C structure, I have one which is -7/4, and the other one which is +7/4. So by theorem 2, I know that N does not bound a negative definite four manifold. Good. Half the job is done. Now I can reverse the orientation. Minus N has the same correction terms. Wait, no. Sorry, I was getting ahead of myself. a different statement that I need to prove. It's exactly it. Sorry. Minus n has the same correction terms because correction terms swap sign, well, they flip the sign when you change the orientation. So d of minus n in the T0 spin C structure is plus 7/4, and the other one is minus 7/4. So the theorem no. Sorry, I was still right. Yeah, so the theorem, the sum of the 2D invariants is 0. So equality holds here, but they are not 1/4 and minus 1/4. So it does not bound the negative definite W. Now, I flip the orientation. It has the same correction terms, so the statement still applies. So it cannot bound a negative definite or manifold. And the statement that it does not bound a definite manifold is equivalent to the fact that it doesn't bound a positive definite one or a negative definite one. And if it, and that an n bounds a positive definite for manifold if and only if minus n bounds a negative definite for manifold. So since we proved that neither n nor minus n bound a negative definite for manifold, this proves the statement. Using the huge black box that is up here. And you may wonder, well, you just spent a lot of time over the past 3 lectures telling us that, or convincing us that correction terms are rather hard to compute. So there's some effort here in actually computing things. Maybe you can ask Sarah how you compute these things, because she knows. But there's an algorithm due to Oshvat and Szabo that has been reinterpreted, refined, reproved, I'm not exactly sure, by Nemeti in the context of singularity theory. And that is vaguely related to one of the exercises that I've given on Tuesday that I'm not going to use. But you can compute correction terms of Seifert fiber spaces using a maximization procedure similar to the one that appears in Elki's theorem. Yes, Andres? So this -3 is because I want that the sum of the 2 correction terms is 0. So when I flip the orientation, I get the same connected sum to 0. So yeah, that's a good point that maybe I should have made, that this part is somehow the boring part, and this is somehow the interesting part. So finding this was a bit hard. Once we found something, correction terms were sufficiently far apart, we just had to find, well, we knew that we had some way of shifting it down. So for the technical part of the proof, for the proof, having that shift of -3 is exactly what you need to have equality in the sum of the 2 correction terms. I have no clue of what happens for different values of 3 in that statement. I know that, well, for sure, if instead of -3 you put any positive number, then you bound something negative definite. And I don't know about anything else. Are there other questions? Yeah. Another good remark. Thank you, Filippo. So their examples are all integer homology spheres, which is better in many, many, many ways. And our example is not rationally homology cobordant to their examples. Otherwise, it would be a bit trivial. With the current technology in instanton theory, our example is not reachable with their techniques. And vice versa, what we are using cannot say anything about integer homology spheres. Actually, we're going to see that in a second. Yeah, there are differences of Seifert spaces.
So there are no reducible examples.
Man, you're hitting the remarks that I should have made and I keep forgetting making. There's a theorem of Livingston from the 80s that says that every three-manifold is rationally homology cobordant to an irreducible three-manifold. So you can substitute that manifold with something that is rationally homology cobordant to it and that it's irreducible. And there's a theorem by Myers that says that you can even suppose that you can even find something hyperbolic.
But there are no explicit examples. This is the point.
You can make Livingston. Livingston gives you an algorithm to turn a surgery representation of a three-manifold into an irreducible one that is rationally homology cobordant to it. Myers' theorem, I would be surprised if this were explicit. To be very concrete, I don't have a concrete example of something that is rationally homology cobordant to this that satisfies either of the properties. But yeah. Right. Any more questions or remarks that you want to steal from me? I can see that Vitalis is there, that he wants to ask a question. N with itself? This, wait, N with itself. So the obstruction that I have does not work. As far as I know, it could bound a rational homology ball. Could be two torsion in the rational homology cobordism. I don't have a proof. I don't have this proof either, but what do you mean you can stabilize it with? If you do that, the obstruction still kicks in. If you add like 3 copies of P, it bounds. If you bound, yeah. With 3 copies of P, yeah. Other than that, I don't know. I was happy that we found one example. Maybe step back. So the proof is the proof of theorem 2 is maybe going to be similar to something that you can do with Elke's theorem for integer homology spheres. This is what essentially Filippo's remark was about, or Filippo's question was about. If you take y is an integer homology 3-sphere, and y is the boundary of a negative definite 4-manifold. Then the correction term of y in its unique spin C structure is non-negative. And for instance, well, this is, again, one of the exercises in half an exercise, or twice an exercise. One can compute the correction term of the Poincare homology sphere. This is 2. So this implies that d of minus p is minus 2, which is negative. So minus p does not bound a negative definite format. And how do you prove this? Well, this is proved by Elki's theorem plus the Urshvat-Szabo inequality on correction term. Because we know that this is bounded from below by C1 square of S plus B2 minus of W for every spin-C structure on W. And when we maximize this right-hand side, then we have the maximum over all characteristic vectors in the lattice H2 of W with intersection form plus B2 minus of W, by 4. And Elki's theorem tells us that this maximization leads to something that is always non-negative, and actually tells us that it's negative, that it's 0 if and only if the lattice of, well, the intersection form of W is diagonalizable, in the same way that we proved Donaldson's theorem. The only small caveat is that you have to prove that the intersection form of W is unimodular if its boundary is a rational homology, is an integer homology sphere, which is again an exercise that maybe I'll give this up for this afternoon. And this is at least 0 by Elki's. So this is OS, and this is Elki's. And it's somehow, the proof is also going to be loosely related to one of the exercises that I given a couple of days ago, that if you have a rational homology sphere that bounds a rational homology ball, then you have a certain amount of correction terms on this homology sphere that vanish. I'm not going to write it down because it's not particularly relevant, but it's related to that. So, how do we actually prove this? The statement smells a lot like Elki's theorem, so we want to try and apply Elki's theorem in some way. But I need to make a detour. We've talked a lot about bimodules in Emmanuel's talks and in Liam's talks. So I want to join in. A bimodular lattice is a lattice L with discriminant 2. Or with determinant 2, which means I can take any matrix, any gram matrix for it, and the determinant of this gram matrix is going to be 2 or minus 2. Or equivalently, I want that if I take the dual lattice and I quotient it by the lattice, then I get Z mod 2Z. And this is called bimodular, but it has absolutely nothing to do with bimodules. It's just that it's bi for 2, as opposed to unimodular. And the claim, actually, this is going to be an exercise this afternoon, but it's an exercise that I encourage you to do during Emmanuel's talk. So if Y is an integer homology RP3, and W is a 4-manifold whose boundary is Y, then the intersection form of W is bimodular. Sorry, Emmanuel. So we're trying to algebraize the statement, make it even more algebraic. And this is the first step. This tells you this gives very strong restriction on the set of lattices that we need to consider. But in Elki's theorem, we need to work with something unimodular. And we need to work a bit for that. Small parenthesis. There is a version of Elki's theorem for lattices that are not unimodular. This is due to Owens and Strellet. It's one version of the theorem. Unfortunately, it's not the version that is enough for our purposes. For a long while, we thought that it was. And then we surrendered with Kyle, and we decided, OK, let's drop it. And then we realized that we could do something else. And that version of the statement is still not enough for what we need. And, but I wanted to mention that there is a generalization of Elki's theorem to lattices that are not unimodular. It's just not the one that we need. Right. And the other thing, I think I did mention, I did mention that on this group, which is sometimes called the discriminant group of L, so maybe this I should call the determinant of L. On disk of L, if L is non-degenerate, meaning essentially if this group is finite, there is a bilinear, symmetric bilinear Q mod Z valued form and this form is the equivalent or the algebraic counterpart of the linking form on H1 of W. So if L is Q of W, then this, I will call it lambda L. Then lambda L corresponds to the linking form on Y, where Y is the boundary of W. It's more of a moral correspondence than an actual correspondence, but yeah, this is true. And the fact is easy to prove is that there's a unique such form, so symmetric, bilinear, non-degenerate, Q mod Z valued form on Z mod 2Z. And maybe the cute proposition, which is part of an exercise, but part of it is an exercise. But if L is bimodular, then L plus L embeds in a unique U a unimodular lattice. Maybe fancier way of saying this is if L is bimodular, L plus L has a unique unimodular over lattice, or is a sublattice of something. And the idea of the proof is that over lattices of L plus L are sublattices of L dual plus L dual. If you have any overlattice of L plus L, it sits in here. Yeah. Yeah. Let me think of core rank 0. Thank you. Yeah. When I say overlattice, I think about something. Yeah. Core rank 0. Thank you. And in turn, sublattices, so I'm looking for something that sits in between, I call it U, okay, let's call it M, and L dual plus L dual. M is really a bad name, but whatever. So if I have a subgroup that sits in between these two, this is the kernel of, this is the preimage of a subgroup of the discriminant group of L plus the discriminant group of L. And actually, M is unimodular. If and only if the subgroup G, maybe let's call it GM, is a so-called metabolizer for lambda of L plus L, which means that G has size, so this is a finite group, and its order is the square root of the order of the discriminant group. So order of GM, so M metabolizer. If and only if, by definition, GM squared is equal to the order of the discriminant of L plus L, and lambda L restricted to GM vanishes. This is Lagrangian subspace in the discriminant group for the 3 people in the audience who do symplectic geometry. And I think that this is a nice exercise. So what's the point? The point is that on the discriminant of L, we have a unique non-degenerate QZ Q mod Z valued form. And the discriminant L plus L is the direct sum of 2 discriminants. And in there, you have a unique metabolizer. This is a group of order 4. You don't have to look that far. You can just check. You have 3 subgroups. And you check, oh, there's only one on which the intersection form can vanish. And it does vanish. Well, the linking form vanishes on that one. And you have the unimodular lattice that you want. So now, the thing that I wanted to say is that we want to use Elke's theorem. So we want to think about characteristic vectors and covectors. And in particular, I want to think about the set of characteristic vectors of U. And I want to restrict them to characteristic vectors of L plus L. And I want to understand who this person is. So, small digression. And I'm under the assumption that things are that L is bimodular and U is the unimodular, the unique unimodular sublattice. The char of L splits into 2 classes. Let's say char plus and char minus. I'm not going to go too much into details, but depending on the congruence modulo 8, of xi squared. There are 2 classes. If I recall correctly, my notation, this should be the set for which xi squared plus B2, well, plus the rank of L is congruent to -1 mod 8. Maybe let's say +1 mod 8. And this is the one for which they're congruent to -1 mod 8. But I might be off by 1 in this notation. No, I think I'm, whatever. I think I'm right. And why does it even make sense? Right? This kind of makes sense, even without knowing how this congruence exactly works. This makes sense because this set given by one characteristic vector plus shifts by 2L dual. And 2L dual, I mean, L dual is just L union a shifted copy of L. Because the determinant is 2, so the index of L in its dual is 2. So when I take the quotient, I have two cosets. I have L itself, and I have some shift of L. And this corresponds to one characteristic covector plus 2L, and this corresponds to one characteristic covector plus this Z plus 2L. So this decomposition corresponds to two cosets of L inside L dual. And the point is that this restriction maps onto char plus of L times char minus of L union char minus of L times char plus of L. What am I saying? I'm saying that there are two types of characteristic covectors on L, and I want to understand when they glue together to give me a characteristic covector on the unimodular over lattice. And this happens only when you mix types. Back to three manifold. Three manifolds, let's think about what this means in terms of three manifolds and in terms of four manifolds. I'm thinking I have a spin C structure on my four manifold W, whose intersection form is L. And I'm looking at the restriction of this spin C structure onto the boundary. And this is the element in the discriminant. Well, this is more or less this congruence class. I have two spin C structures, and I have one set of spin C structures on W that restricts to one spin C structure on the boundary and another set that restricts onto the other. This is the geometric side of the statement. And I want to know if I glue my four manifold, well, let's say to itself. Let's suppose that I can do that. I want to know when does the spin C structure that I fix on the boundary extend to both sides. And this is the algebraic translation of this question. I'm asking a gluing question for spin C structures, and this is the algebraic version of that question. So I always have in mind that L is the intersection form, and that lambda is the linking form. This is my dictionary. And characteristic vectors are spin C structures, and restrictions are restrictions. Or rather, the projection from L to lambda L corresponds to the restriction of spin C structures from the four manifold to the three manifold. So might be that I'm ready to prove the theorem. Let me double check, but I think I'm ready. So I have my L. So suppose that Y, my integer homology RP3, is the boundary of W, where W is negative definite. Then I call L Q of W by an exercise that is somewhere up, somewhere, I don't know. Oh, yeah, the exercise that is up there on the second board. L is bimodular. By the Auschwitz-Savoy inequality, if I take, so I have char plus of L, and I have char minus of L, and I will always use psi plus for elements in here and psi minus for elements in here. If I take max of psi plus of psi plus square plus the rank of L divided by 4, this is a lower bound for one of the two correction terms, and let me call it T plus. And if I do the maximization on the other side, I get a lower bound for the other correction term. Because in my correspondence, I said that one spin C structure on Y corresponds to restrictions of elements here, and the other corresponds to restrictions of elements here. So what do I have? On the one hand, by Elke's theorem, so I also have that L dot L plus L embeds in a unique unimodular lattice. And what do I have? Well, to consider this quantity here. So d of y t plus d of y t minus. This is bounded from below by the max of psi plus square plus the rank divided by 4 plus the max of psi minus plus the rank divided by 4. This inequality applied twice. So this is the max over pairs psi plus psi minus of psi plus square plus psi minus square plus twice the rank of L divided by 4. And now the magic up there in the penultimate board tells me that I can glue any vector of the form psi plus with a vector of the form psi minus, and this gives me a characteristic covector in U. So for every psi plus in L and psi minus in L, then psi plus direct sum psi minus in L plus L is a characteristic covector for U, the unimodular over lattice. And vice versa. Any characteristic vector on U is of the form psi plus plus psi minus, or psi minus plus psi plus. So when I take the sum over all these pairs, oh, and also, like L plus L, this is an orthogonal direct sum. So psi plus and psi minus are in two distinct vectors, so they are pairwise orthogonal. So the square of psi plus, one sec, let me finish the sentence. Yes? I said the restriction. So if I view so if you take a characteristic vector on U and you restrict it to the submodule, to the sublattice L plus L, you get a characteristic vector of the sublattice. And they are like this. And then I'm saying you can actually go back. If you have two characteristic covectors, one in char plus and one in char minus, and you take the two of them in the two distinct summands, yeah. So using this implies that this maximization here is actually the max over psi in U of psi squared plus twice the rank of L, and twice the rank of L, thanks to Diego's question, is the rank of U, divided by 4, and L keys tell me that this is at least 0. So this proves the first half of the statement. That sum is at least 0 if you bound something negative definite. Does this make sense to some people? More or less. Now for the other side, if you have the equality in the statement, then all this chain of inequalities is an equality. So you actually have that dy t plus dy t minus is equal to 0, but also that this is equal to 0. So this means that U is unimodular. U is diagonalizable. By Elke's theorem, by the other half of Elke's theorem. Now the trick. Took me a very long time to come up with this trick, but L plus L in, so suppose that U is diagonalizable, so this is just Z to the 2n, the diagonal intersection form. This is an index 2 subgroup. And an index 2 subgroup is the kernel of a homomorphism to Z mod 2. And the point is that there are not that many morphisms from Zn to Z2Z. And okay, small technical assumption, you can suppose that L has no -1 summons. You can throw away the -1 summons. So you can suppose that there are no vectors of square -1 in L. And at the level of this morphism, this implies that no generator of Zn is sent to 0. Because the only thing of square 1 in here are the generators, the basis generators. And they are in the kernel if and only if they're sent to 0. Duh. So if you impose that restriction, there is really only one morphism. There's one homomorphism from here to here that sends no basis element to 0. It has to send all the basis elements to 1. And so there's a unique phi. And then you can deduce, well, if I have a unique phi, I can compute its kernel. This is a rank 2n lattice of determinant 2. I can compute really explicitly what this lattice is. And this lattice is never is never irreducible, is never reducible if n is larger than 1. Meaning it cannot be split as a direct sum of two lattices. So in particular, it cannot be of the form plus L. So this means that the only L that is possible is for n equal to 1. And in that case, L plus L, actually, L is equal to minus 2. And then you have some bit of extra work, but not too much work, to say that once you know L is minus 2, you can sort of go back with the inequalities and show that the correction term of y have to agree with the ones that are predicted by this lattice, meaning that you have to do a maximization process, but this becomes a one-line computation, and once you've done that computation, you show that if equality holds, then the correction terms are very restricted. And I think I'm going to leave this as an exercise during for the tutorial this afternoon, which is at 3:30, and I think I will stop here.